Welcome back. We're going to talk now about the second part of the material, permanent remediation opportunity for Onondaga Lake sediment. This is the current sediment plans for Onondaga Lake, the dredge and dump method as we call it. Honeywell will employ or deploy a dredger out in the lake which will dredge up the sediment in a slurry, about 90% water, 10% sediment. That'll be pushed up a tube, which is a screen line. You can see here the fairgrounds, comes around and actually goes up to waste bed 13 in Camillus. Once there, the sediment will be put into geotubes, which will be used to dewater the sediment, pull the water out. The water actually will be treated up there by a water treatment facility and sent back down to the Onondaga County Metro for further treatment before going back into Onondaga Lake. We're going to bring the human health risk assessment back in just for a moment. We're talking about longer term risk here, but to just kind of get an idea of what permanent remediation can do to some of the components in the sediment, we're going to look at the components in the sediment the HHRA determined were the most risky for cancerous and non-cancerous effects from inhalation of those chemicals. For cancerous effects, these are the results from the HHRA in percentages. Of the overall risk that was defined in the HHRA for waste bed 13, we'll find that there's only 5 organic compounds that contribute greater than 70% of the risk to cancer. Those compounds are ethylbenzylene, naphthalene, tetrachloroethylene, dichloroethylene, and methyl butyl ether. This subset of lake sediment we're going to use to see as kind of a test case against current results on permanent remediation to see how well that technology can do on these. Just like the last slide, we can also look at the main contributors to chemical inhalation risk for non-cancerous effects. Turns out there's actually 6 chemicals. A couple of these are similar to the first page that contribute over 70% of the non-cancerous risk for inhalation from the dredging operations. And again, we'll use this to look in a moment at how effective permanent remediation can be on these chemicals. Okay, permanent remediation, our proposal is to use a 2-step process. The first is to address the volatile organic compounds or the toxic organic compounds in the sediment. The second step will address the metals, especially mercury, which also is toxic to the environment and humans. So the first step is chemical oxidation. If you go out there in the literature, their most pilot and full-scale applications to date have been in situ for chemical oxidation. What that means is chemical oxidation has been used without disturbing the material you're treating. In most cases, that's soil and groundwater. The chemicals are pumped into the soil and groundwater and used to treat the toxins that are in place. Per EPA, this is being used for groundwater, sediment, and soil remediation, and has been for at least the last 15 years. It can be applied to a variety of soil types, and it can be used to treat a wide range of volatile organic chemicals, semi-volatile organic, and etc. Anything that is toxic and organic, it pretty much treats. There are several different forms of oxidants that can be used and have been used. They range from what's called permanganate to Fenton's reagent, which is actually hydrogen peroxide. That's what you put on your cuts sometimes to clean them up. Ozone, I think everyone knows what that is, and persulfate. These chemicals, when mixed with organic compounds, will degrade them. This is just a little chemical equation to demonstrate that, with benzene being broken down into carbon dioxide and water. This is a very attractive process because you can go from a toxic organic to basically carbon dioxide and water through this treatment. If there is anything left over that's not carbon dioxide and water, it's very simple organic molecules that can continue to be broken down by biodegradation. Chemical oxidation remediation activity. This is an example. We're picking a firm called Isotech because they have a lot of material on their website. They've been in operation for 15 years doing in situ chemical oxidation treatment. They've treated more than 1,000 field scale locations actually pilot and field scale, and they've completed those to date. Again, there's case studies online that can be looked at, and the interesting thing here is over the last 15 years they've treated millions of cubic yards of soil. Remember, for the lake, we're looking at treating 2 million cubic yards of sediment. The point here is that this company can treat more volume than is in the lake right now over the last 15 years, over thousands of different locations, than to treat 2 million cubic yards all in one location at one time is very doable in a time frame of 5 years or less. Here's some results that have been taken from these case studies from Isotech. And again, what we've done is we've taken those organic compounds we identified in the first couple slides in this section, and we looked at the case studies that Isotech has and looked at the minimum reduction in these compounds after treatment and maximum reduction. You'll notice that at a minimum, 60% of the organics were destroyed, and as high as 95%. Organic remediation or oxidation remediation of organics is very, very effective. What we want to do is start thinking out of the box. We obviously do not want to treat the sediment in the lake. That would be very, very complicated. And again, most of the examples so far have been in situ or in the environment that the toxins are in. Honeywell is planning on pumping the sediment out of the lake. What we're proposing is you actually treat it after it comes out of the lake. To show you an example that this can be done, is there another company called Verotech that already has equipment and is already doing ex situ treatment of soils with toxins. The interesting thing here is that they have a piece of equipment that can do 400 to 800 tons of material a day. If you scale that up about 2 to 4 times, you can treat the 2 million cubic yards of sediment in the Onondaga Lake in 5 years. The technology for chemical oxidation continues to improve. This is an example. A company called Enchem just recently received a grant from the EPA to advance the chemistry for chemical oxidation. Their process is specifically designed to treat very, very hard to treat hydrocarbons, naphthalene, other chemicals that the basic chemicals we talked about before do not do as well on. These advances will only improve those numbers we showed on the other page as far as destruction capability, and will benefit as far as higher efficiency and lower cost overall for a project like this. Onondaga Lake sediment ex situ chemical oxidation next steps. What we want to do is propose a series of steps to basically work into a full-scale treatment of the sediment for Onondaga Lake. First and foremost, we should measure the sediment oxidative demand. This is basically going to establish how much chemicals are needed to actually treat the sediment. Then perform a bench scale test on a 10% sediment slurry to estimate the efficiency of the chemical process, and then finally construct the pilot sediment treatment facility on waste bed B. This is where the sediment will first come off the lake after the dredging operation, can be treated right in line before it goes up to waste bed 13. Advantages we see of chemical oxidation are permanent reduction in toxicity. This is going to lower that overall risk in the long term. Lower sediment consolidation area water treatment costs. Remember, there's a water treatment plant to treat the water up on waste bed 13 after the slurry is pumped up there. The water will have less toxins in it, and that will lower the costs of the water treatment plant. Those savings can be used to pay for the additional chemicals you're going to use for chemical oxidation. The nice thing about doing this ex situ is that instead of in the ground, which is very, very hard to treat chemicals because you have to make sure you get the chemicals, the things you're putting into the ground equally dispersed and get it there quickly before they decay. This can be done out of the lake very efficiently in a mixing chamber and be very controlled and have very high efficiency. The other nice thing here is once the sediment's treated, if it's low enough toxicity at that point, it might be used for other applications. The next stage of the treatment, we're just going to briefly talk about a technology developed. We call it the mercury sponge. It's called thiol SAMS. It's a nanotechnology engineered material. The great thing about this is you throw it in water, in this case the slurry, and within minutes it'll absorb 99% of the mercury. in the slurry. It has a capacity of 60% of its own weight, so it's very, very efficient. Again, 100 grams of this material will absorb 60 grams of mercury. It operates over a wide pH range, and it's not susceptible to most organics, so it can be used with a chemical oxidation process very well. And we're suggesting that this can be put in during the ex situ chemical oxidation step. Finally, just an overall picture of how this might look like. Again, we have our dredging operation, 10% slurry, and as soon as that comes off the lake, you introduce a mixing chamber. Here we've shown 110 per hour drum mixer, just to kind of give an idea that these chambers, these mixers already exist. Once the slurry gets pumped in there, you would add oxyzone C or some similar chemical formulation to destroy the organics, and then add thiosams to absorb the mercury. Once that's done, the treated slurry can be pumped back up to the waste bed if so desired. And again, at low enough levels of toxicity after treatment, it might be used as CAP or some other application. Permanent remediation is complementary and can be placed in line with the current plan and will not be disruptive to the overall cleanup of Onondaga Lake. Thank you.